Let's start the magnetic effect of electric current part 2 according to 2021 boards. So let's start. Come with me. Friends, welcome to my channel. My name is Corey Harshal. So I hope you are fine. So let's start our video. So in previous video what we have discussed. So we discussed magnetic field, we discussed a magnetic field, right hand thumb rule, etc. we have discussed in previous video. So this is the part 2 of magnetic effect of electric current. So in this video we are going to discuss magnetic field through circular loop, magnetic field through solenoid, and force on current carrying conductor in a magnetic field. So let's start our video of this part 2, magnetic effect of electric current. So start from circular loop, magnetic field through circular loop. So consider a conducting circular loop. But first of all, we need to, what is a wire? So we know what is a wire. Wire is a straight line that passes the current. So when we move the wire, means when we turn the wire in this like shape, so what we can become, it become a circular slope. So like this, the wire is turned in a loop like structure, means it is turned and manipulated in a circular loop. So it is, we can show that it is the circular wire, so we can say it is a circular loop. So when current is passed, ion fillings arrange in a concentric circles. Means if we connected a loop like this, and when we pour the ion fillings around it and on the circuit, then the current flow from that, it will look like this. Yes, it will look like same like a magnetic field. So it is a look like a magnetic field, and here we can say that all are look like a concentric circle in the edges, and here also like this. So by this we can say that a circular loop is also a magnet. So magnetic field lines of the field produced by a current carrying circular loop. So what are the specific points of this? Yes, for example, magnetic lines of force are concentric circles around the conductor. Yes, means it is a conductor. We know the wire is a conductor, means circular loop. When the current is flow, it look like yes, north to south, north to south. So by the both sides it look like as, yes, here is the straight line, here all are the magnetic field lines, or look like here in the concentric circles. So this is the feature of magnetic field due to current carrying circular loop. So what are its specific points? The specific points are, at the center of current carrying loop, the magnetic field appears to be straight line. Yes, here they didn't show, but here it looks like a straight line at the center. The magnetic field produced by a current carrying wire at a given point depends directly on the current passing through it. Means the current carrying wire, this is depends on the current flowing it. Means the wire, means the circular looped wire is already depends directly, means it is directly proportional to the current passing through the this wire. I hope you are getting understood. So this is the magnetic field due to the current carrying circular loop. So let's move another way. What are these? Yes. So if a circle, means we know that a wire can connected in a circle or in very another ways. So this is connected in a hexagon for a experiment, means it is a phase clock rule. So we saw circular loop, but if we connected wire like this shape, means like a 1 2 3 hexagon or pentagon, so and the current flowing charge is clockwise, means clockwise, it is a clockwise. So what happens if the current flowing is clockwise and the wire is situated like this, and when we on the circuit, when we pass the current clockwise into this shaped wire, what happens? Yes, it look like this. So it will look like this in a clockwise. So by this means current is flowing clockwise. Then what is its magnetic field? So its magnetic field for one wire, it is like this. Here already shown in the figure. So by this what we can understand? By this we can understand the north side is outer the body. Means north side is outer the body of the wire, and south side it is the inside the wire. Means if the magnetic field is produced in this like a wire, in wire it can produce like this in a straight wire. But what happens when the wire is turned in that shape? So it look like so this. Yeah, simple. Means the magnetic field look like this, but same directions are same. Only the difference is it look like this, but direction is same. Means inside the wire, means inside a magnetic field of wire, it is south side, and outside of the magnetic field wire it is north side. So this is the difference in a clockwise. So what with the anti-clockwise? This is the clockwise direction of the force and the current. So what if we move the current anti-clockwise? It means from this. So what we can understand, the direction also changed. Means when we change the current flow, when we change the direction of current flow, the so now north and south sides means all the poles of a magnet or magnetic field, it can also be changed. Means direction of current is directly proportional to the yes to the poles of a magnetic field or magnetic area. So in anti-clockwise, outside are south side and inside it is north side. Yes, understood? So let's see. Now there is a important point that we can say face clockwise. Means it is the face clock. Means what means how we can remember this both. So if the current flows in anti-clockwise, the magnet pole is north. Yes, means the magnet pole should be north. Means by N we can understand the magnet pole is should be north. Means it is anti-clockwise. So it is anti and it comes N means north. Means anti-clockwise current is the direction of pole is north. And in south means it current flows in a clockwise, the magnetic pole is south. Means clockwise current. Means by the design of fairs we can understand the south magnetic pole is occurs when clockwise current is flowing. So this is how it works. It is known as face clockwise rule. So let's start our solenoid. Means a current flow through the solenoid. So what is a solenoid? Let's see. Means we know the wire looked like X. But what if wire we turned in look like this? Yes. When wire is situated, means wire is occurred in a coil, it is known as a solenoid. So the next point of this chapter is magnetic field due to solenoid. So we covered magnetic field due to circular loop. So the magnetic field due to solenoid. So the solenoid is the coil of many circular turns of insulated copper wire. Means the metal is to copper. So it is a copper wire wrapped closely in a shape of cylinder. It's called a solenoid. Means the copper wire is wrapped coiled in a shape of solenoid. So shape of cylinder. So is called as a solenoid. So let's move it. It is a solenoid means coil of copper wire. So coil of copper wire. So what happens? 1 minute. So this is solenoid. So look the solenoid like a ring-like structure. It look like slick. Means if a solenoid is we imagine the solenoid in a ring-like structure, it look like this. So what happens when the current is flowed in a solenoid? So it look like it means when we imagine the solenoid like a ring-like structure, means the sequence of rings in a cylinder. When the current is flowed in a solenoid, it look like see this. Yes, means it is look like a in a ring there is a current flowing here. Means one ring of solenoid is same to same as a circular loop. So this the current is look like this. So magnetic field means coil carrying electric current. Means if the current is flowed like this, it looks like a north to south, north to south. Means it is like the bar magnet also. The bar magnet also look like same. Means when the current is flowed through magnetic bar, so it look like so north to south, north to south. So solenoid act as a north to south. Means solenoid act as a bar magnet, magnetic field lines through a magnetic bar. So this is the coil carrying electric current. So if in an exam it asks find the A, means A and B are given to the name of the solenoids, so find the current of A. How can we find? So in A it is a south, means we know that it looks like north to south, north to south. So in A, when the current is flowing, means when in a structure, means the pattern of magnetic field around the current carrying solenoid is same as that of a bar magnet. Yes, it is equal to the bar magnet. Means one end of solenoid behaves as a magnetic north pole. Yes, one pole of a solenoid behaves as magnetic north pole and while other behaves as a south pole. So this is same like a bar magnet, I already told. The field lines inside the solenoid are the form of parallel straight lines. Means the field lines inside the parallel sides. Inside the solenoids are parallel straight lines. Means they are parallel. The field is uniform inside the solenoid. Means all the current direction is uniform. Means same inside the solenoid. A strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnet like a soft iron, or when it is placed inside the coil, the magnet so formed, it is called an electromagnet. Means by the solenoid we can also structure a electromagnet. So if in a magnetic field is produced inside a solenoid, then when we magnetize a piece of magnet, means when we put a piece of magnet in the solenoid or inside the coil, it so form a electromagnet. Means when circuit is on, yes, when circuit is on, we put a iron, soft iron, or any that magnetized any material, then it is through called electromagnet. So by the magnetic field due to solenoid, the electromagnet is formed. So hence we can also call solenoid as a magnet. Yes. But hence the electromagnet forms. But in electromagnet, if the circuit is on, then only the iron pills attract the solenoid. But if circuit is off, then all didn't attract. They remain constant. Means they remain stationary. So this is solenoid electromagnetism. Yes, the process by the solenoid produce the electromagnet. It is called electromagnetism. Means when we put iron, soft iron, or any magnetic material, it can form a electromagnetism phenomenon. So by this, a solenoid produces a electromagnetic rays. So this is, we can say, solenoid means magnetic field due to solenoid is a magnet. So let's move ahead. Yes. What is the direction of force that is exerted on a current carrying conductor kept perpendicular in external magnetic field? Means in external magnetic field, in a cell, means there are two magnets. One magnet means first magnet, the north is here, and the south pole of other magnet is look like here. And when the current is flowed, and a conductor, a current carrying conductor is exerted in this field, magnetic field. So what is the direction? So how can we find the direction of this? By the Fleming's left hand rule. So let's situate in a easy area. Means let's understand the Fleming's left hand rule in easy method. So come with me. Going through it, first look out the electromagnet. What is it? An electromagnet consists of a long coil of insulated copper wire wrapped on a soft iron. Means insulated copper wire is a solenoid and soft iron is a magnetic material. Magnet formed by producing magnetic field inside a solenoid is called electromagnet. I already told. So let's move to the Fleming's left hand rule. Means we know what is electromagnet, but we put the force, then what is the direction of force? So it is known as force on current carrying conductor on a magnetic field. Means now to find the Fleming's left hand rule. So why do we find what is necessary of finding the Fleming's left hand rule? So let start it. Means a force on a current carrying conductor in a magnetic field look like this. Means a current carrying conductor when placed in a magnetic field experiences a force. Yes, means a conductor is placed in magnetic field, means a insulated copper wire we already seen in a electromagnet. So it look like this. So the features are the current carrying conductor exerts a force when a magnet is placed inside its vicinity. Means look like this. Means why we use Fleming's left hand rule? Because when the current carrying conductor is drawn to the perpendicular to the other magnet, means the magnet is perpendicular to the current carrying conductor, then it forces a magnetic force and move away. Means it move away the other conductor and the magnet, it moves away. Why it moves away? But in 8th standard we already learned the object move away by a external force. It can't move by its own. So there is a force in that. The force is called, of course, magnetic force. Means when we put a current carrying conductor in a magnetic field with the perpendicular to a magnet, then it forms or exerts a force. That force is called magnetic force. By this we can understand the both current carrying conductor in a magnetic field directs a force, means place a force. It is known as electromagnet or force on current carrying conductor. But we didn't know what is the direction of field. Means we know that in a magnetic field the force is exerted, but we didn't know the direction of force. So to calculate, to know the force, to know the direction of force, then V is given by Fleming's left hand rule. Means the scientist S.T. Fleming gives the rule. So by calculate, means to solve this problem or to find the direction of force, we need to use Fleming's left hand rule. I hope you are understanding it. So by this we use Fleming's left hand rule. Yes, Fleming's left hand rule look like this. It is the hand of Fleming. So the thumb represent by the direction of force. Thumb represent the direction of force. Then the index finger represent the direction of magnetic field, and the middle finger represent the current, direction of current. So how to memorize, how to fit it is in a memory? So by this F, M, C, means the force F, magnetic field M, current C. So we can already memorize this by the father, mother and child. F, M, C means the force, direction of force stands for father, magnetic field mother and current child. So the Fleming's left hand rule forms this. I hope you getting the Fleming's left hand rule. So let's say in a theoretical language. Stretch the first finger, middle finger and thumb of the left hand such they are perpendicular to each other. Yes. If the first finger points direction of external magnetic field, the middle finger forms the direction of current and thumb forms direction of conductor, means direction of force. So this look like this. I already told you. It look like this. So it forms. So let's solve this in a numerical. Means if in exams they ask question, find the force, the magnetic field and direction of current is given, find the direction of force. How we can use the Fleming's left hand rule? Let's come with me here. So the direction of magnetic field is north to south, means the direction of magnetic field is given north to south, and the direction of current is given flow of positive charge. Why they use positive charge? We know that electricity is negative charge, but in it is a conventional. We use only conventional. We didn't use the actual flow of current. We only use the conventional flow of current, that is positive charge. Don't use the actual flow of current, that is negative. Only use the direction of flow of positive charges, that is conventional. So let's move. The direction of current is downwards and the direction of magnetic field is, yes, north to south, means here. So let's use the, yes. So the direction of current stands for index. Sorry, current stands for middle finger, means middle finger is downwards. Yes, middle finger is downwards. Then the magnetic field is look like this, means it look like west to east to west. And what is the direction of force? The direction of force, of course, it is upward. Yes, you can use it. You can use by your hand. Means here it is look like this, but when we put the middle finger downwards, then the magnetic field like yes, then the always the force we can get direction of force upwards. Yes, by this we can find direction of force. So let's move ahead. So we finished our part 2 of this magnetic effect of electric current according to 2021 boards. So what we have discussed circular loop, we have discussed solenoid, we have discussed due to solenoid how the electromagnetism forms, and we already discussed the Fleming's left hand rule according to current carrying conductor in magnetic field. So we have discussed 4 to 5 topics and the important crucial topics of this chapter. So we finished our part 2. Part 3 we released shortly in time. So if you like this video, then like the video and share with your friends and subscribe to my channel. Bye bye.